Welcome back. Today we're going to be looking at advanced numeric types in Python. So of course, we've used numbers before in Python, including the integers, but it turns out that all these numbers are a derivative of numbers, which is this abstract base class. So you can't actually have a number, but you can have subclasses of your number. And so if you ever want to create your own type of number, maybe you want to implement quaternions or octernions, then you derive them from the number class. We've also got the basic ones, so int, float, and complex. And these ones you don't have to import, they're just there already. And int and float are very common, but we'll have a look at complex. Fractions, which you can use to represent rational numbers, and decimal, which allows you to do fixed point and floating point arithmetic with decimal numbers rather than binary numbers. So the first thing we're going to do is from numbers import number and check if 8 is a number, and of course it is. See if the string 8 is, and it's not because 8 is actually a string, so it's not derived from number. And then to check if 8.0, which is a float, is a number, which it is. Then we're going to start with integers. So we have all of these arithmetic operations and all of these bitwise operations which we can perform on the integers. And so it kind of just sets x to 7, y to 3, and then performs all these different operations, which hopefully you've seen before. And then the bitwise operations, including OR and XOR, shifts, and the NOT. So we have these floating point numbers, which can represent any real number. And we can just apply the arithmetic operations to them again. But if you try doing bitwise operations, then you get an error. And so of course, all ones you've seen before. However, you can see there are these limitations here with precision errors, where the value is not quite precise enough, and so we end up with errors. And for fractions, therefore, like a third, which you can see are not represented so well here, we can import fractions. And so what we can do is we can represent all these numbers as fractions. So we've got 2, 1 divided by 2, 0.75, and a third. And you can see these are all fractions represented exactly. We can convert pi into a fraction, and of course there is a limit to the amount of precision we can have. So we had to convert it into this fraction. But if we want to limit the denominator to be maximum 1000, then we can just limit the denominator, and it sets the denominator to 113, which it thinks is the best. And if we did 100 instead, then it would give us 311 over 99, which is quite close to the value of pi. So if we try doing it with this cos of pi by 3, which is a half, but is not quite perfect. So if we just limit the denominator anyway, then it figures out that half is very close and very small, and we don't need all of these additional numbers to try and represent it. We can also do arithmetic operations with fractions. So you can see that all the results are fractions, except here, where we try cube rooting 7/8, which has a 2 on the bottom, but the top is irrational, and so can't be represented as a fraction, so it returns a float instead. We can also then have decimals. And so we have this decimal 3, 2.8, 1.58, which you can see we've got from a string, and 9.6E4. And you can see that 2.8, it represents as this almost 2.8 value. So again, converting from a string means that we get the exact value. And if this exponent here were larger, then it might represent it in standard form. But for now, it's just doing it as this integer. We can also convert fractions from decimals, but we can't convert decimals from fractions. And that's because if we had, for example, a third, then how would you represent that as a decimal? It would just fail. We can also represent pi as a decimal, and you can see that has a very long series of digits, which is probably why we were getting floating point errors earlier. There's also this thing called context, And so you can see the default precision is 28. It will round half even, which means that it rounds the top half. If a number ends in, for example, 0.5 and you want it to 0 decimal places, then it will round up. But if it's below 0.5, it rounds down. And you can set that to round down or round up. It's got the minimum and maximum exponents in terms of precision, capitals, clamp, and then some flags. And then these traps say that if it's an invalid operation, you try dividing by 0 or you get an overflow, raise an error, because otherwise it will just try doing it anyway. So we're actually going to set the precision to 4, and it looks at the minute as though that's done nothing, but when we then do operations, it converts them, all of them, to exactly 4. And this could be slightly irritating if you do 2 operations and your precision is a specific amount, and then you do another one and you want it to change. So again, order can often matter when you're looking at the precision. And a general rule of advice is to set the precision to slightly higher than you need and then turn it down just at the end. If you are doing values and you wanted everything calculated to 3 significant figures, you might set precision to 4 and at the end convert precision back to 3. And here we just set it back to 28. And we do all these arithmetic operators with decimals. And you see we get all these answers which are decimals, even when some of them don't work out that nicely as decimals. Then we can use complex, and we're going to import CMath, which is a library for doing complex math. There are many ways of initializing complex numbers. So you can see you can initialize it from integers. Complex numbers you can just type in. You can have a string, but there can't be any spaces in your string. You can just have the imaginary part, and then you can type in real and imaginary parts, or you can use fractions and decimals to initialize it, as has happened here. So again, we can do all our arithmetic operations, but you'll notice there are a couple missing. So there's no floor division, because it doesn't really make sense, and therefore there's no modular arithmetic, because again, that doesn't really work with complex numbers. And you can see that both parts are floats. Another thing that's interesting is that if we try doing sine with complex numbers, you see we get an error, and so it says here, must be real, not complex. And that's where the CMath comes in, because we can take the sine of complex numbers and it returns complex outputs. Another couple of functions that exist in CMath that don't exist in normal math are polar and rect. Polar takes the complex number 12 minus 5j and represents it as 13 and then this angle. And rectangle takes something that has a radius of 4 and an angle of pi by 3 and returns it as a complex number in the form a plus bj. So as an overview, we've got all these different types, whether they're integers, floats, fractions, decimals, or complex numbers, and of course they are all numbers. So hopefully you've enjoyed this video. You've learnt about some data types you might not have already known about, and you'll be able to use these in future projects when you're working with decimals, fractions, complex numbers, or even just floats and integers. And I'll see you again, same time next week. Till then.